So then moving on to chapter 6, we talked about momentum. And we define momentum to stand as lowercase p, and that is equal to an object's mass times that object's velocity. And as you can see, I have drawn arrows, and so yes, we are dealing with vectors again, unlike energy, which is a scalar. So we have momentum that could happen in the x direction, could happen in the y direction, could happen in the z direction, but it is a vector, and this is linear momentum. We'll talk about angular momentum later. But that it is a measure of the mass of an object and the velocity of an object. So, again, you can have velocity in the different directions, and therefore you're going to have momentum in your different directions. And so you're going to have to be addressing this with regard to components like we were doing before when we're looking at projectile motion and forces and all that fun stuff. So the idea of components will pervade the rest of the entire class. Okay, is that fundamental of an idea, that you have to look at the motion along those different axes completely separately and independently. Okay. Another thing to think about is that if you look at the definition of force, force is equal to, a net force, is equal to an object's mass times the acceleration it experiences because of that net force. Now, what is the definition of acceleration? It's the change in velocity divided by the change in time. If the mass is not changing, then what is m delta v? M delta v is equal to m v final minus m v initial, and this is p final, and this is p initial. So that means that m delta v equals delta p. So force, the net force an object experiences, isn't just its mass times its acceleration, but it's also equal to its change of momentum over a given time. And this is actually the original way that this was formulated back when Newton was thinking about things with regard to forces. He was thinking about an object's change in momentum in some time period. Okay. So an object will be changing its velocity because of a force, and therefore changing its momentum, because all objects have mass. We're talking about objects, not talking about photons. Then an object's momentum will change because of some force acting on an object. And if we simply bring this delta t over here, F net delta t is equal to delta p, then we can actually rename this and call it the impulse. And so some force acting on an object over a given time period is going to be equal to its change in momentum. And so this equation right here is called the impulse momentum theorem. Which is just another way of rewriting the conceptual statement of something caused the object to change momentum. And that something was a force that was applied over a given period of time. Okay. The other thing that we talked about today with regard to momentum is that if you have an isolated system, meaning no external forces are involved, then the momentum of the system beforehand is equal to the momentum of the system afterwards. Pf is equal to Pi, that being the conservation of momentum. Okay. The momentum before is going to be equal to the momentum afterwards. And I'll go through the example I did in class briefly to look at this and see mathematically how we got this. And let's imagine that we have an object moving towards an object, and some other object moving towards that same object. This one we'll call 1, and this one we'll call 2. So we have m1 and we have m2, and before they hit, we have a velocity for each of them. So we have v1 initial, and we have v2 initial, and then after they hit, they're going to have the same mass still, so we have m1, and we have v1 final, and now we have v2 final. Okay? So let's look at what is happening here with regard to the impulse momentum theorem, and if we look at the force on particle 1 due to particle 2, F of particle 2 on particle 1 is equal to, times delta t, is equal to m1, put an arrow on here, m1 v1 initial, m1 v1 final minus m1 v1 initial. Let me redraw this over here to get it out of the way. So F delta t is equal to the change in momentum. So I have m1 v1 final minus m1 v initial. And then if I look at the other situation, where I have what's happening to particle 2, that's equal to its change in momentum. Now, what does Newton's third law tell us about these two forces if we're in an isolated system? We know that they are equal in magnitude and opposite in sign. So that means that we can then relate these two things so that we have this one is equal to the negative of this one. So F21 delta t must therefore be equal to negative F12 delta t. Delta t is just delta t. It's the same time that both objects are experiencing the forces because we're talking about the interaction of those two objects. And so F21 delta t equals this, F12 delta t equals this, so m1 v1 final minus m1 v1 initial is equal to negative m2 v2 final minus m2 v2 initial. So if I just multiply the negatives through, that means this equals minus m2 v2 final plus m2 v2 initial. And if I want to make everything positive, I can bring this over to this side, and I can bring this over to this side. And so I can rewrite this as m1 v1 final plus m2 v2 final is equal to m1 v1 initial plus m2 v2 initial. And this, what does this say? This says that we have momentum before and after, and what about them? The final momentum, momentum of the first ball or object, and the momentum of the second ball or object, final, is equal to what they had to start with. And so this is the idea of conservation of momentum. If something has zero momentum to start with, if the system we're talking about has zero momentum to start with, then it has to have zero momentum to end. So if you're out there in space, and you are spacewalking, and you got detached from your space shuttle, okay, and you have a wrench, and you want to get back to your space shuttle, right now you have no momentum at all. But if you throw the wrench away from you, you give momentum to that object, and it gives momentum to you. In order to conserve momentum, the amount of momentum that you have going in this direction has to equal the momentum that the wrench has going in that direction. Because you had zero momentum to start with. And so, you'll throw the wrench, and since it's lighter than you, it's going to end up going faster, the nature of the MV combination here, and you're going to go slower in the other direction, but you'll make it back to the ship. So everything will be a-okay. But that's the idea of conservation of momentum, and the next class we'll be talking about this with regard to collisions.